And now to finish up the confidence interval example, we're going to construct a 90% confidence interval, the estimate for the difference between the two population proportions. So that was the spending with dollar bills versus quarters. And so we're going to look at what do the results suggest about our claim about people spending large denominations relative to spending small denominations. And just a little side note, remember some of the common z critical values for confidence intervals are for a 90% confidence interval, it's always going to be 1.645. For a 95% confidence interval, it's going to be 1.96. And for 99% confidence intervals, it's going to be 2.575. And so these we can always use for confidence intervals of proportions. And now, so I'm just kind of plugging everything in from those formulas from before, which are those right there. And so now just to find that margin of error, I'm just using that 1.645, plugging in p hat, so that first sample proportion. Then this will be the opposite of that sample proportions, since I just do 12 out of 46, 46 minus 12 to get 34, that total 36. Here's the sample proportions for the second sample, so the quarter sample, 27 out of 43. Subtract that, 16 out of 43, there's our opposite, divided by 43. Once we would evaluate all that, we should be getting a margin of error of about 0.161387. Then we just plug in what we had from there. So this p hat 1 minus p hat 2, remember that's the 12 over 46 minus the 27 over 43. Just getting that difference as a decimal, which comes out to about negative 0.367037. Subtract the margin of error. There's our lower bound for the confidence interval. Same idea, just now adding the margin of error, and there's our upper bound of the confidence interval. So what we conclude is the confidence interval limits do not include 0, so implying there is a significant difference between the two proportions. In other words, that they're not equal. So there does appear to be sufficient evidence to support the claim that money in large denominations is less likely to be spent relative to an equivalent amount in many smaller denominations. So same conclusions, but just keep in mind that may not always happen with confidence intervals versus hypotheses tests. I want to show you can get that same conclusion using an applet. So this time you're going to use the two sample z interval for proportions. And let's see, just save time and typed in the same information here. I just click on begin analysis. Now I want to come down to the bottom, and I got to make sure I'm typing in my right confidence level. So type in 90 for this one. Make sure I'm looking at the spent variable in this case, perform inference. It gives me lower bound and upper bounds, and it gives it in percentages, so negative 52.8%, which is the same as negative 0.582. And then for the upper bound, negative 20.6%, which is the same as negative 0.206%. And again, just keep in mind when you type in the data, you don't type in the success and the total. You type in the success and failure. And a way to double check is the applet finds the totals down here for you. Alright, and so this is just a little extension piece for why these procedures work, so I wouldn't worry too much about this, but have it here if you want to see just kind of why these procedures work. So the distribution of p hat, so sample proportion, can be approximated by the normal distribution with that mean of the sample proportion with that standard deviation, square root of p1 times q1 divided by that sample size. Then the difference can be approximated by a normal distribution also with the mean of the difference of the two proportions of these population proportions. And then the variance, which goes as follows: the variance of the first sample plus the variance of the second sample, which notice we're kind of assuming equal to the population data here. And the variance of the difference between two independent random variables is the sum of their individual variances. That's a key reason why that works. And so that preceding variance leads to this standard deviation, where notice we're using the pooled proportions this time, then equal to the square root of all those. And we know that the distribution of p hat 1 minus p hat 2 is approximately normal, with the mean of essentially the population difference of their proportions, and standard deviation as shown above. So the z-test statistic has the form that was given earlier. Now, when constructing the confidence interval estimate of the difference between two proportions, we don't assume that the two proportions are equal, and so we estimate the standard deviation as this, where the only difference is now instead of using those pooled proportions, we're using the sample proportions. Right, and then in the test statistic, you notice we're using all those sample proportions and use the positive and negative values of z for two tails and solve for the population P1 minus P2. And the results are limits of the confidence interval given earlier.